would like to invite Professor Samir Thakur sir to introduce Dr. Rodrigo sir.
One of the our Dr. Rodrigo G Amorim. Well, you know him as a renowned physicist, but just in case, he has completed his bachelor's from Rio de Janeiro, master's from Sao Paulo, and of course going further to achieve his doctorate in the same field from Sao Paulo. His area of expertise is in the exact and earth sciences, followed by many awards and title and yes. So I invite Dr. Rodrigo Garcia Amorim. Hello, can you hear me?
Yes, sir. Yes, sir.
Can you see my screen?
Yes, sir.
Okay. Here is early morning. It's 3 a.m. in Brazil. Sorry for this small problem in my computer, because here we don't use this Zoom. I just upgraded the software and it works. Today, I am talking about modeling materials through density functional theory. I'm from Brazil. First of all, I'm very far from you now. Here is India. You have the equator here. In Brazil, the tropical country, like there. I live in the state of Rio de Janeiro, 100 kilometers from Rio, in an industrial city called Volta Redonda. And my university is, I think, is the third or fourth biggest university in Brazil, and have a lot of advanced campus. I work in this building, particular this one. This is a computational physics course. We have almost 50,000 students and 3,000 professors and lecturers in this university, close to an important river between Rio and São Paulo. In my city, we have a big steel industry, and we have this engineering school. Oh. Can you see my screen? Hello?
Your screen has turned into black, sir. Dark.
Yeah, here.
Almost there.
Wait. Why? It's black. Open again. Wait. And now?
Yes, sir. Perfectly visible, sir.
Yes, sir.
Okay. But let's start the main topic here today. I talk some important points before we start some materials model. First of all, what's a computer simulation? This is an important issue to address here. Computer simulation is using the computer to solve numerically some equations that control a given process. Computer simulation today is present in all branches of science and increasing every day. We can see computer simulations in finance, engineering, weather forecasting, biomolecules, materials, flight simulations. Some examples here, for example, for aerodynamics, forecasting. We have examples in bioscience, biomolecular simulations, and the stock markets. But how about material science? Here is a diamond, okay? And this diamond, the question is, what is the material made of, or what's the building blocks? If we look into this diamond, we can see that inside the diamond, we have a crystalline structure. And this crystalline structure is formed by atoms. And atoms has electrons, okay? And the question now is, what's the rule for forming this material or making their building blocks hold it together? We keep this question, but computer simulation, we can turn in three pillars. The most important is the experiment. We observe the nature facts, and with this observation, we create theories, models for these facts. In general, we have solution for a few special cases, and we should have approximation for some models, for some theory. Simulation, we can solve the model, test the theories, we can provide results where it's very difficult, dangerous, or some simulation that is impossible to have experimentally. And these three pillars are connected, and it's important working together, okay? But for start a simulation, the first step is we have a very well-defined problem. Once we have a problem, we have a well-defined questions. Once you have this problem and these questions, what's the interaction model that we can use? What's the building blocks that we mentioned before for that questions? For example, we can use a model as a molecular dynamics or density function theory or Monte Carlo or Hartree-Fock perturbation methods. The second one is, once you define the model, we should have the algorithm to solve this model, or numerical solution for the model, or numerical equation discretization. And finally, we should have some tools to analyze the simulation and results. Let's back to the diamond. Here, okay, I have a problem. I would like to simulate a diamond, and a small diamond with 64 carbon atoms. For 64 carbon atoms, one carbon has 6 electrons. We have a 448 body problem. This is not easy. But how to describe a many-body system? Okay, we have atoms, we have electrons. Okay, for describing this system, you need quantum mechanics. When we can consider a time-independent Schrödinger equation like this, or a stationary equation as this eigenvalue problem like this. We have the Hamiltonian, we have the eigenvalues, we have the wave functions. The Hamiltonian is composed by the kinetic terms, the kinetic energy for electrons, the kinetic energy for the nuclei. This is kinetic terms. In the interaction terms, we have the interaction between electron nuclei, between electron-electron, and the nuclei-nuclei. This is the interaction terms. Each problem has a more suitable method to be employed. And an important point is the length and time scale. For example, here is a plot from time versus length. If you are working in the time scale of 10 minus 15, and the size is 10 minus 9, you are in the electronic regime. For that, we should have density functional theory or another theory that treat electrons. If you are in this time 10 to the minus 9 and the size 10 to the minus 6, you have a mesoscopic regime. And you have also a macroscopic regime. For that one, you treat with statistical mechanics and thermodynamics, etc. Time scale is important, and we have an anybody problem. Anybody problem is with this Hamiltonian. But how we can solve this many-body problem? This is the key. Our system, we have electrons and the nuclei move into the system. But if you analyze, the electrons move more faster than nuclei because the mass for the nuclei is very huge compared to the mass on the electrons. And we can have the first approximation. If you have, for example, an electron and this nuclei, and you have the electron, if this nuclei moves, the effect is instantaneously the electron takes their position. This is due to the difference of time scale. We can consider the nuclei fixed, and we can solve the electronic problem. Or we can ignore the electrons and solve the nuclear dynamics. This is also possible. The nuclear dynamics can be decoupled from the electron due to different time scale differences. Okay, but we can back from this Hamiltonian. Due to these differences, we can make approximation called Bohr-Oppenheimer approximation. Our total wave function in terms of R from the nuclei, R from the electrons, and time can be decoupled in the electronic wave function times the nuclear wave function. We note here that the electronic wave function has a point common and R. R in this equation is a parameter, okay? It's like this. For each R, we can solve the electronic problem. Okay. With this approximation, Bohr-Oppenheimer approximation, we can split, for example, the electronic Hamiltonian, and the stationary equation for solve is this. We can solve this equation in different ways. For example, Hartree-Fock, density functional theory, perturbation methods, variational methods. But something is happened with my presentation.
Yes, sir.
Can you see my
No, sir. No, sir. Your screen has again got black, sir.
Yeah. I think after some time, maybe due to the connection.
Yes, sir. Please share again.
Yeah. Wait. they can hear me perfectly?
Perfectly audible, sir.
Yes, sir.
Okay. Problem is just the presentation sometimes. Let me see here. Screen. Can you see now?
Yes, sir.
Okay. And we have this total Hamiltonian. Do this different time scale difference, the ions and the electrons. You can make this approximation that I mentioned before. And in the electronic terms, we have R, big R is nuclei position as a parameter. Okay, we can solve this problem, but for solve this problem now, we don't have the nuclei because we have the electronic problem, but our electronic problem is 384 bodies. The previous problem is 448 problem. Now is a little bit more easy, but is complicated. Keep it complicated. Okay. Let's thinking about precision versus number of atoms. For example, for ab initio methods, the methods for solve, for example, the electronic problem, we have a big precision, but the cost, the computational cost is very high. It's expensive cost. And we can handle with few atoms. If you go to tight binding methods, semi-empirical methods, is 3 orders of magnitude faster than ab initio methods. We yet have considered electrons. We can increase the number of atoms, but the precision is less than ab initio methods. And we can have empirical potentials without electrons. No electrons is involved, and we have these classical potentials. Okay. Example here. This is simulation of my student. This is water. This is contra ion, and the graphene with a pore. Okay, we have here classical molecular dynamics, 10,000 atoms, and we solve the Newton equations for that. We can handle this in a laptop or in a small computer without problem. It's not complicated. But let's back to our electronic problem. I show one way to calculate this. The electronic problem today, I am talking about density functional theory for solve the electronic problem. Okay. The density functional theory was developed basically by Walter Kohn, Hohenberg, and Shan. And Kohn win a Nobel Prize in 1998 with John Pope. Okay. And this is the 3 most important papers for DFT. We have this 2 from the theory, and this one is more cited than the theory. This is the approximation. We have more than 10,000 citations. This is old, okay, has, I don't know, 2 years. It's more than this today, okay? And this is the citations for these important references, that DFT. But what's the main idea? We have the wave function. If you have the eigenvalues and eigenvectors for that equation, the electronic equation, we have all information for the system. And all information, but the wave function is a 3n degrees of freedom object. But all information that we have here, we have in the electronic density. Electronic density is more easy object. We have 3 degrees of freedom. And in the regular quantum mechanics, we have the external potential. We have the wave function, then we can calculate the observables. This is the many body problem. For 3 degree, for the density, we can have the density, we can have the wave function and the external potential. We can solve this with any one body problem. I show how to do this in practice. And this is the charge density definition. Okay. The DFT is based on Hohenberg-Kohn theorems as the following. The first theorem is the external potential felt by electrons is unique functional of the electron density, ρ0, and the total ground state energy, E0, ρ0, is a minimum for exact density, ρ0. Okay. All properties of the many body system are determined by the ground state density. This is the important. Okay. I will show a very quickly proof for these 2 theorems. But first, let's see these assumptions. Given 2 external potential, V external and the V prime external, necessarily we have to differ more than a trivial constant if they do not lead the same Hamiltonian. This potential leads to different states, psi 0 and psi prime 0, respectively. Let's start this equation, T plus U plus V external, psi0, E0, psi0. T electronic plus U plus V prime external, psi prime 0, E prime 0, psi0. Okay. This is the ground state energies for 2 different wave functions. Okay. Problem. If we consider that these wave functions are similar and we subtract these 2 equations, we have this result. Okay. V external minus V prime external psi0 is equal E0 minus E prime 0 psi0. And the meaning of this is given 2 external potential V external and V prime, in the case where psi0 is equal psi prime 0, this can differ at the most by 1 constant, which violates our initial hypothesis. Thus, we conclude if you have an external different of V prime external, this leads to psi0 different of psi prime 0. Okay. Now we still show, given 2 different states, this do not lead to the same electron density. Let's consider non-degenerate case, and the ρ0 is equal ρ prime 0, and consider 2 different Hamiltonians with their external potential, V external and V prime, respectively. And according with highly Hertz variational principle, we can write this equation. Okay. Note that we have psi here and psi prime here, according to highly Hertz variational principle. And since psi prime is not eigenfunction of the Hamiltonian, we rewrite 8 in terms of 8 prime, like this. Okay. And we replace in this equation, and we can write this E0 equal E0 prime plus this term, this integral dr n prime V minus V prime. We can do the other way around. We can make the same thing and write this other equation, but note the previous E minus E0. Now we write the prime in terms of H, 8 prime in terms of H, and we can have this equation. If you subtract this 2, or add these two equations, we have this result, E0 plus E prime less than E0 plus E prime minus the integral N0 minus N0 prime, the external minus the external prime. And the initial assumption is N0 is equal N prime 0. And we found this equation that is absurd. And the conclusion is two different non-degenerate ground states necessarily leads to two different ground states densities. And we can now write the function of energy like this. Okay, we have psi0 T electronic plus U electron plus the external psi0. And since the energy of the fundamental state is uniquely determined for the electronic density N0, and we use the principle of Rayleigh heights, we can state that E0 is less than En for n different of N0, and the energy for the fundamental state can be found varying the density. Just minimize the functional, okay? We can rewrite that equation in this form. Here we have the universal functional for many body system plus this integral dr vn, okay? And the summary for Hohenberg-Kohn theorems is the electronic density determined univocally psi per contradiction. We showed that E0 and is minimal for N0. The universal functional F8K is the same for non-relativistic and the column system. Electrical density determines univocally the external potential. This is what you show until now. Let's go for another point. What's missing? The Hohenberg-Kohn theorems don't show how to make it in the practice. For that, we should go to constant equations. Let's consider a system of n non-interacting electron system at a external potential Vs. We can write Hs Hamiltonian like this: Ts, no interacting system, plus Vs. Okay. Writing the energy functional, Es is equal Ts plus integral dr Vs n, according to the Hohenberg-Kohn theorems. After that, we can have the definition from the charge density. Ns is sum over all electrons, the phi square. Okay, and the Schrödinger equation for n independent particles is given by this: the kinetic energy plus Vs, phi is Ei. Here, the equations are independent, not many body, but is many one body problems. Okay. What's important here that phi are completely different of psi. Okay. These are eigenfunctions for individual non-interacting electrons. Okay. But let's map the many body problem for any one body problem. We have the electronic problem, is this part. Okay. Now I use sum and subtract the kinetic energy for non-interaction system, and sum and subtract the Hartree potential. Okay. This is the kinetic energy of classical electrons and the Hartree energy. Okay. The definition for heart-free energy is this. And we can see, rearranging these terms, that the function of energy is Ts plus V external plus U. The energy, this kinetic energy for electrons, for interaction electron-electron, minus Ts minus Us. Okay, this is the universal potential, and this is the definition of exchange correlation energy. Okay, this is the definition of exchange and correlation energy, appears naturally when we make this mathematical manipulation. Okay, everything that you don't know is in these terms. In this term, this is we can call this ignorance is found in these terms. Now we should minimize the energy functional with some constraint. Okay, delta E equals 0. The constraint is the number of electrons is given correctly. Okay, and this constraint, we can have the Lagrange multiplier mu is a chemical potential. The functional is given the energy functional minus mu times integral d dr n minus n. This is the equation that we should minimize. If you're looking for the minimum for this equation, we can have the functional derivative for each term, okay? And we can have the functional derivative like this. We have delta E, delta N minus mu, delta Ts, delta N plus E square integral dr and over R minus R prime, the external plus Vxc, exchange correlation potential, okay? We write the chemical potential like this. We can have the definition of Vxc, the delta Exc over delta N. And finally, we found the Vs and one body problem, okay? This is the quantum equation that is very important for simulations. This is the equation that we have inside the programs, okay? In practice, what we have? We have our charge density. We calculate this constant potential, or Vs, or Vks, solve the one body problem, calculate the next charge density, and we ask if the input charge density is equal the charge density calculated through some criteria, 10 to the minus 5, for example. And if you achieve this, we calculate the observables. If not, you calculate this until you achieve the criteria. This is a self-consistent field, okay? But there is some missing point. We have this exchange correlation potential. We can have the local density approximation, is the most simple approximation, okay? The energy at some point, for example, R, is taken to be equal some exchange correlation energy of a homogeneous electron gas. Imagine the system, and we can have the system split in small pieces, and each pieces will have gas, okay, homogeneous electron gas, and you sum over all gas. Oh, the LGA is very good for system homogeneous. Okay, LDA is exact for system with uniform electron density, and we expect that be very good for system that the density varies smoothly. The other approximation that we use is GGA, or generalized gradient approximation. There is two types of GGA. The first one is semi-empirical, is fitted by experiments or some materials in interest. The second one is non-empirical, satisfies some constraint. We have a lot of GGAs, okay? One of them is PBE, Purdue, Burke, and Enzenhoff. This type of GGA is type 2, non-empirical, and satisfies some constraints. For example, the PBE, they have the correct asymptotic limits for limited case where the electron density very slow or quickly, the correct scale on behaviors for the spin and the uniform density, and obey the lower limit for Oxford limits. Okay, and there is some modification of PBE, Sol, PBE. When they change, they have other constraints, and they change this Oxford limits. Okay, the difference of LGA and GGA: LGA is local, and GGA depends on the density, the local density, and also the gradients. Okay, it's more complex. For some cases, LGA gives good results, better than GGA. For example, due to the error cancellations, is more easy in LGA than in GGA. But this is a very depends the system, depends of a lot of things involved. Okay, but okay, I talked about GFT, and there is some program that calculates this self-consistent field. The response is yes. There's a lot of codes. More than this is just a little. But in particular, are you talking about Siesta code? Siesta code, if you wanna, this a distribution, is a fully open source GLP license since 2016. If you want to see the project, we have this link. This is the page. Okay, you have documentation, pseudo potentials, code. We can download in your computer. Okay. Why we choose the Siesta? Siesta is a very efficient code. Okay, and I think it's the pioneer code using order n algorithm. Here, this CPU load versus number of atoms. You can see order n means if you increase the number of atoms, the load is linear scaling. Okay, for some other system, the load is the complexity for the algorithms n3, for example, and is very costly. Okay, and the success of Siesta is based on the atomic the basis sets. They use this LCAO, linear combination of atomic orbitals. We have this, if the wave functions is we have the radial part like this, and we have our harmonical spherical harmonics. Okay, and this is a natural basis for the orbitals. This is one the points for Siesta. We have advantages, is very efficient. We have this reduction of CPU in memory, and we can straightforward for physical interpretation, population, etc. For trait vacuum, this is very, very efficient compared to plane waves codes. The disadvantage is the convergence of the base set is not the unique. Sometimes it's tricky to have a good base set. And the responsibility is on the user. Okay, we can have we can take a look in some system that is more complicated, and the base set is, if you have a good base set, you have a good description for your system. This is the point. Siesta in the last years launched a lot of new versions. Here, Siesta is implemented in Fortran. Okay, they have this performance. If you have a big cluster, you can handle 10,000 atoms. There is a very interesting parallelization algorithms. They parallel over orbitals, is parallel over K points. There's some solvers. They have the energy optimization. They have this molecular dynamics, this ab initio molecular dynamics. Also has this trans-Siesta code and the linear scalar regime, this order n. Okay, and this base set is natural for you have this no equilibrium problems. Okay, what's the Siesta features? You can have, for example, the standard constant equation. Siesta calculate this, that I show you, calculate this constant equations, okay, using the GGA, LGA, van der Waals. Okay, the master newest version has the van der Waals D3, for example. They use the multiple zeta basis set, polarization. They have this real space projections, K-point sampling, Brillouin zone, spin polarization, non-collinear spin, etc. And the recent versions, we have this time-dependent DFT also, okay? And with Siesta, we can compute total and partial energies, atomic force, stress tensor, electric dipole, a lot of charge, optical properties, magnetic moment, band structure, many other possibilities, okay? Okay. Now, I give a short example using Siesta. This is electronic transport anisotropy of C-doping borophyrin. Okay. This is the motivation for this work. They synthesized the borophyrin, and they argue that this system is anisotropic. Okay, this is one phase. They synthesized this on top of silver, okay, and they have this another phase B1, 2, and K3. They have these three phases, and the goals here is study the electronic and transport properties of borophyrin in two phases, and check the stability, study the STM fingerprints for the Doppler system, investigate the electronic transport anisotropy. Okay, for this I use inductive function theory as implemented in Siesta code that I mentioned before. No equilibriums, green functions, mesh cutoff for each system, K point, exchange correlation functional, PBE, GGA, numerical basis set, DZP, and force criteria 0.01 EV per angstrom. Okay, this is the B12 and K3. This is my unit cell. Okay, this is I calculated this with Siesta, and I obtained the structural parameters A and B and C, and here my error compared to this reference is 0.19%, and for Q3 is 2.53%. I choose this unit cell, and I have these 3 sites, okay? But the site 1, there is some equivalent here, okay? I just show the more stable. This is the formation energy for B12, and we have these 2, and the B121, the site 1 is most stable, and K3 we have these 2, and the most stable is this K3 1 also. Okay, 1 and 4 here is equivalent. 2 and 3 positions is equivalent. Okay, we did this energy comparison. After that, we calculate this electronic properties. For example, for pristine without doping is the black curve. We have a metallic system. Here, the Fermi level in the 0. We have levels crossing the Fermi level. Okay. What happened when you dope it with boron? Boron has 1 electron less than carbon. The effect is we have this band shift and the break symmetry. Okay, we have a split of this state and shift down. Okay, and for example here this crossing shifted down, shifted in the symmetry points and shifted down due to the electron missing. Okay, for Q3 we have the same. The blue one is the pristine system, and the K3 doped is the orange. Here we have the opposite. The states goes up, and we have some splitting due to the extra electron in the system. Okay. It's very interesting if you calculate the total charge density for B12. We have this covalent bond, okay, and in this direction we have the metallic bond, okay. The same for K3, okay. When we have, for example, a carbon, this covalent bond change to more ionic bonds, and the metallic bond keeping there. And for K3, we have a similar behavior. The question is, we have for the band structure, we can see the anisotropy for the electronic properties, and this is the second evidence of this anisotropy. Okay. After that, we model the STM using the Tershov-Raman model. We have our band and our density of states here. Okay. In this model, we consider a tip, and this tip has a s orbital, and dIdV is proportional to L DOS. What we can do here is integrate the states from the Fermi energy for some certain energy, okay, for have this model. Here we integrate from EF until the positive energy. We have this from the negative energy or positive, you have occupied the states. Here we have the pristine B12 and the doped one. Okay, this is the covalent bond that we showed before, and when you have the carbon atoms, they change the signature. Okay, compare this with the experiment is very close. Okay. The final application here is the transport And we saw some evidence for anisotropy transport. We did the two setups. The first setup, we have, for example, X, transport through this direction, X, and the second, the transported through the Y direction, okay? For this, Siesta can handle if it runs Siesta. We calculate the transmission function. Transmission function means the electron probability for incoming electron from the left side passing through the scatter region and reach the right side. If you integrate this this function, we can have the current, IV current, okay? We have the transmission. The black one is transmission for B12 TX. B12 TY is the dotted line black, and the dotted one is green, TX, and the TY is the dotted green, okay? If we have this probability, this transmission is a probability. We can, for example, take this probability for center energy, for example, 0, and project this probability into the atoms. We call this as local current. It's not the current, but is the projection of the probabilities. For B12, we can see here if you project this for pristine case, we have the current spread from the system here. We have in the hexagonal here, and the current passing through the covalent bond, okay? We calculated the B12, but in this direction, the Y direction, okay? Or this is, we can have the current into the stripe, for example. When we have the Doppler system, what happened? The current is localized into the carbon atoms and the Doppler region. When we have in the other side, we can have, for example, the current more concentrated in the inner part of this stripe, okay? We calculate this anisotropy in terms of IV curves. We can see the IV curves from minus 0.6 to 0.6, and we can have different IV behaviors for B12. When you have the Doppler system, this anisotropy increase for B12, and in case of K3, this anisotropy decreases. This is interesting because we can control the anisotropy with the carbon doping. The conclusion of this application part is we have the stability of B12 and K3 C Doppler system. We show the band structures and the effect of include one electron and extract one electron through boron and nitrogen doping. And we show the nature of the bonds, metallic or covalent, depends the directions. And when we have this doping, they become ionic. We simulate the STM images, demonstrate these fingerprints when you have this doping, and finally we show this anisotropy, the transport anisotropy properties. This was published last year. This is my junior student. This is my master student, former student. Okay, and thank you very much. This is my research group. There is some missing people here. Thank you for the agents for the supercomputer Santos Dumont. And this is my research group, NanoSim, and I open for questions. Thank you very much for this opportunity. Hello.
Now session is open for discussion. Sir, there are few questions.
Okay.
Hybrid functions are yet to be implemented. How to predict the energy band gap as a function mentioned by you?
Could you repeat a little bit louder because I can't hear it exactly?
Yes, sir. It is also showing in screen that question from chat. Hybrid functional are yet to be implemented.
Hybrid function.
Yes, sir.
What is chat here? Chat more. Chat here. Okay.
Yes, sir.
Okay. This first question?
Sir, Bhanu Chetri, sir. By Bhanu Chetri.
We have a lot of questions here.
Yes, sir.
I think there is a lot of new implementation Siesta code, and hybrid functionals is one of them, but it's not for the users now. But if you enter in the Simuni website, they say that it's coming soon. But I have a colleague from Siesta group. They are developing this, but it's not open for people yet. But this is a good point, because the functional that we have today is not good for estimate bands. We should have this hybrid functionals or go beyond DFT with other approach like GW and etc. and using different codes. The second question. About the chemical potential. Depends what we can show. For example, chemical potential, for boron we can calculate from the atom, or you can calculate from the small structures. When you calculate this formation energy, we should have in mind which ambient we have. We have a rich in boron or poor in boron. We can make different approach to have this, and this will imply a different ways to calculate the chemical potential. Okay. What about the trend IV at higher voltages? This is a good question. The no-equilibrium grease functions use as input the equilibrium theory. Which equilibrium? DFT is equilibrium theory. The point is, for large voltages, this model is not good. Because of that, I just calculate close to the Fermi energy. I think more than 1 EV is too much for the equilibrium input that we have. Our input in this theory, I didn't say about transport, but our input is DFT. And if we have a non-equilibrium theory using input as an equilibrium theory. Because of that, we don't go to large voltage. It's clear? Is current voltage calculated with Siesta? Yes. Which version is more stable? Depends. The stable version today is 4.1.5. Okay. But a stable version for van der Waals, if you the old version 4.0.2 is very stable one. Using, because from the 4.1 they change the input from Siesta, and it's a little bit more complicated. The more simple case is until 4.0.2, but I use both. Okay. If you want some papers, just let me know. Just write me an email. I can send papers, some papers that I have. The stability, okay. When it comes to p orbitals compounds where we can't use U correction tool. I don't understand this question. If you have some explanation, this correlation, this question, when it comes to p orbital compounds where we can't use U correction tool, is about the correlation. I don't understand this. Or you are saying about LDA or GJ plus U. I think for this case, with p-orbital, you don't need. For binding energy calculation, Becker-Monk function can be used. The binding energy is a good point. For example, we have this problem of a base set. I don't know if they know this BSSE, because the base is not complete. We can, for Siesta calculation, when we have a binding energy, we can use this BSSE correction to keep the base set not complete, but better. Okay. This problem we don't have in plane wave codes.
I would like to thank Dr. Rodrigo G Amorim sir for his valuable talk on computer simulation that is definitely going to help us for future and academics. Now it's time for lunch break. So I request all the participants to rejoin the meeting by 3 p.m. for the hands-on session. Thank you.
Okay, thank you very much.
Thank you, sir.
Thank you.
Bye-bye.
Bye, sir. Bye, sir.
Bye-bye.
See you very soon, sir, again.
Okay, bye-bye.